Hello again, welcome back to the practical part of the course, and now we are planning to make some work on our practical exercise number 1. I have already uploaded parameters of the practical exercise, so practical exercise 1, and now I'm opening it, and you can see that for each of you we have different parameters: beta, gamma, number of symbols, number of samples. There is also one parameter same for everybody called symbol time interval, and as a signal we are going to use your name and surname converted into plus or minus 1 depending on the letter type. So-called consonant letters such as L, N, S, G, R, and so forth are all plus 1s, and vowel letters are all minus 1s. So you need to repeat your name and surname so that you have 15 symbols, right? That is going to be your signal. So also during this practical exercise, I will show you what happens if the channel filter is not really, how to say it, a raised cosine type filter or non-ideal one, and basically you will see how the phase, nonlinear phase, can affect the signal form. So for the practical exercises, all of them, I believe, that we'll encounter in this course, we will use either MATLAB or Octave, whichever is available to you. It's simple that in our country, for our local students, they do not get access to MATLAB license, so we have to resort to free alternative, yes, such as Python or...
Sorry, I have a question. Are they the same language? For example, if I have MATLAB, can I use the same, do the same on MATLAB?
Yes, they are exactly the same language. So the same code can run in MATLAB and in Octave. Well, I believe there can be some differences, but they are compatible in any way, yes. So we are going to start a new program, new script, right? And usually I make some preparing for clearing console, clearing all the variables just in case they don't interfere with operation of the code. Yes, and we'll make it as a practical exercise 1 Chan model, for example, right? So don't forget that you need to start your file name with a letter rather than number. You also cannot use white space, yes. So pay attention to the rules of naming the files in MATLAB. MATLAB is very demanding in this particular thing, yes. So this is going to be our first practical exercise, and for that we need some parameters specified in this file. So now we will input all of these parameters, and I have these parameters for myself slightly different, right? But it will work nonetheless the same way for each of you. So commands, just like in MATLAB, can be specified with this percentage sign. So we specify individual, well, not really individual, just specify parameters, yes, because there is also this sampling time, not sampling, but symbol time. So this is actually, well, let us denote it with symbol time. So basically this is the symbol, right? It's not mentioned here symbol, but I will add. These are just parameters right now, but I hope this week I will finish the complete guidance, what you need to do, what are the tasks, what must be in report. Yes, so basically it will be more informative for you. Let's see, for example, how it's done for bachelor level course. Yes. Yes. So practical exercise guidelines. Yes. So they will be like this: what is needed to be done and what must be the contents of your report, right? And some additional notes, some help, yes, you can use during this task. So I will make this during this week, yes. Hopefully I finish it by this week. Again, there is no strict deadline for these practical exercises, so you can send them whenever they are ready, yes, but you need to do as much as you can by the end of the semester, right, which is in June of this year. So let us continue by adding our parameters. So this is symbol time 10 milliseconds. Milliseconds are accordingly minus third power of 10. So we can use this engineering format. This is symbol time. Next parameter is beta parameter for our filter. So this is roll-off factor. Beta, in my case, I had beta 0.6. So you input what is specified for you. This is roll-off factor of filter. Next is gamma parameter. Gamma parameter comes as this constant attenuation, right? And it's accordingly less than 1. So it will show how your signal is attenuated during the transmissions. Accordingly, in my case, I had it equal to 0.5. So this is path loss of channel. Now, next parameter is number of symbols in our impulse response. So I will explain it after I input so that it's understood. In my case, it is 5. So number of adjacent symbols, so neighbor symbols. In lecture, we have mentioned that strictly speaking, this number of symbols can be infinity, right? But in real filters, especially considering we are going to make filter with finite impulse response, we need to have specific finite number of these symbols. So that's exactly it. Number of symbols is accordingly how many neighbor symbols are considered in this impulse response, except for the currently transmitted one. So currently transmitted one is 0, then we have 1, 2, 3, 4, or 5. I don't believe there is more than 5 for anybody of you. So there are only options for 3, 4, or 5 symbols. How much of these side lobe symbols we are going to have? That is this parameter. And the last parameter was number of samples per symbol. So this is number of samples. Going to be, in my case, it's 7. Number of samples per symbol. Again, considering that computer is actually a digital device, and we are trying now to model some analog or some continuous time processes on it, we have to actually sample our impulse response. So that means that it's not going to be this line, but rather than that, it is going to be specific number of samples per this symbol. And accordingly, this parameter specifies how many samples we will take into consideration and basically which we can connect with the line to make this illusion of analog signal, right? So these are these parameters. Now that we have input our parameters, we can start working on our shape of the raised cosine signal impulse response, which will be generated according to this formula, right? So what we need to do now is to actually input it. Please pay mind that here we have this MATLAB sync function written here. The MATLAB sync function is slightly bit different from simple sync function. Simple sync function is accordingly specified. So, for example, sync function of x specifies that we calculate sin of x and divide by x. Now, in MATLAB or Octave, we can read help on sync function, and it says that it is rather in only in MATLAB, right? It is sync function of x is instead specified as sin p multiplied by x divided by px, right? So you need to pay attention here that sometimes in software it can be not like in theory, right? In theory we have here simply x, which may or may not contain this p variable, but in MATLAB particularly it calculates this, right? So in these lecture slides it's already specified in MATLAB option. Now if you calculate it in, for example, manually by multiplying sin and dividing with t, then you need to actually input here p, yes, because as you can see, for example, in cosine we have this p, similarly for any sin, but for now, right now, this is already specified in the format we need to use. So basically it's going to be our formula which we need to input here. But before that we actually need to know on what range this t changes. So we need to have minimum value of t, and we need to know maximum value of t, which are denoted accordingly by the number of symbols, right, and symbol time. So basically that gives us that minimum time is going to be -5 in my particular case, or in general minus n symbols multiplied with the symbol time. So in my particular case, it's going to be -50 milliseconds, right? And the maximum accordingly the same with the sign of plus. So let's say that we specify the time range of impulse response. So as I said, it starts from minus n symbols multiplied with t symbols, and it ends with plus. Oh, I don't write the pluses, it's not really necessary. Unless we write minus, it's a positive number, right? So this is only minimum and maximum, but we also need to specify the step matching our sampling time. Yes, so basically our sampling time depends on, well, we might as well actually calculate it because we are going to need it later anyway. So sampling time is number of samples per our symbol. So our symbol will contain 7 samples, right? So that basically means that we divide symbol time with the number of samples. So that would be sampling time. So in general, what we want to achieve, how it will look like, is this. So we will have our impulse response in discrete form, somehow like this. Okay, so here we need to have 0. and so forth, right? So number of samples per symbol is here. So that would be NSMP. Number of symbols is accordingly number of symbols, which is here. Sorry. Here is the first symbol, the second, the third, and the fifth. The fourth, yes, for example. In this case, N symbol is 4, and it will go the same way into this direction as well. So basically it repeats. It's symmetric, and that's what is most important. That's exactly how we are going to get a linear phase. So you see, for finite impulse response filters, there is a condition under which the phase frequency response is going to be a linear function. That's exactly what we want to do. And the condition is very simple. The impulse response must be symmetric. Yes, if the impulse response is symmetric, then this field filter will always have ideally linear phase frequency response. Yes, that is quite simple to achieve. That means that actually the symmetricity can be positive and negative. That means that we can have either the same signs of the symbols here to this side or opposite signs. Yes, so this is called antisymmetry. Yes, so either symmetric or antisymmetric impulse response will produce strictly linear phase field filter. And that's why we want to have it this maximum value right in the middle. Yes, of course, you realize that we cannot really make a negative time here. So instead, this is going to be our delay. Delay, which we denoted by tau in our first lecture, if you remember here. Yes, that is our delay introduced by this time while we reach this central value of our filter impulse response. It will become more clear once we plot everything, but right now I'm just telling you about idea. So we're going to generate our field filter, which is having the structure without feedback. So basically we have different how to say it, delay units. Each of them delays our value by one interval, by one sampling time interval. So basically it takes the SMP time to transfer signal by one of these memory cells. Yes, so basically this is actually random access memory where we store some values. And here we have these multipliers that's actually multiplying signal with. These are exactly our values of the impulse response. So we can say that this is H0, this is H1, H2, H3, and for example H4. So in order to get a linear phase frequency response, H0 must be the same as H1 or H4, or either plus or minus sign. Similarly, H1 must repeat H3, and in this particular case, H2 is center of the symmetry, which can be either 0 or some specific constant value, right? So that's the idea. After that, all these values are added up together and output is generated. So it takes for this one to reach the output exactly in this particular case of linear symmetry, where we will have this central node set to 1, exactly half of these memory cells. Yes, so basically n divided by 2 NSMP. in our particular case, divided by 2 time units, right? So that's our delay, right? Which must be introduced in this channel model. And for gamma parameter, you have it specified. So delay is being calculated depending on your parameters, and we will calculate it a bit later in further steps, right? So what's this sampling time? So we need to specify it here. Yes, so that is the step. That's how in MATLAB we usually specify a range. We start with minimum value, then step, and then maximum value. Right, so this is our time range. Now, this is array, a vector, yes, for which we can calculate our impulse response. So once I run this code, I can see what's inside this value t, and we can see that it goes from 0.5, yes, up to plus 0.5 with some step. And in the middle, somewhere here is the 0 value, right? So now we are going to implement this formula, yes, starting with this part, according to which we must calculate our filter impulse response. So we are going to denote it with HRC. So calculate filter impulse response. That will be HRC. And accordingly, we calculate it according to this formula. So first of all, we divide with our symbol time. So here, capital T is our symbol time. Then multiply with sync function. So that's exactly how we write it. Sync T divided by symbol time. Right. Next step is this fraction where we have cosine in numerator and this difference in denominator. Now, however, pay attention that when in MATLAB you multiply vector with vector element-wise, you have to do it by specifying this dot multiplication, dot product symbol, right? So this is considered, these two symbols are considered with to be the same symbol for mathematical operation called a dot product, yes, because otherwise it will try to calculate vector product, yes, which is impossible to calculate unless one of the vectors is a row and another one is a column. In that case, it will be a simple one scalar number as a result, which we do not want to be. We want particularly take and multiply each vector value with each vector value from another one. Yes, so basically this sin will produce a vector and this cosine will also produce a vector, and we want to multiply each of the values with one another. Yes, so we calculate it here. For p we write specifically p. Now we have beta, we have t, and we divide it with the symbol. And now we need to divide with this expression, which again is a variable of the vector t. That's why we perform division also with this dot symbol, right? And in brackets we have 1 minus 2 beta. Now we don't put a dot here, yes, with release, because beta is a scalar. It's a single number. It's not a vector of multiple elements. If beta would be number of variable with multiple elements, a vector, I would have to use dot here as well, but it's not. Yes, so divided by the symbol. Now each of these vector values, which is vector because t is vector, needs to be squared. So for that reason, for square operation, we also use this dot. Yes, so it's important not to forget these dots, right? whenever we perform element-wise operations, element-wise multiplication, element-wise division, or element-wise power, yes, or squaring or something like that. When we use functions from vectors, they are already vectorized and accept input as entire vector. As for addition doesn't need this dot either, right? So we no dots here. So it only related to multiplication and division and powers, yes? So basically we now have calculated this, and we can already start and make simple plot to see how it looks. So in order to see that in discrete domain, I'm going to use stem function. So for stem function, x-axis is time, and the y-axis is HRC, which we have calculated. We might as well add grid lines and well, labels. X label, that is going to be our time, seconds, and the Y label is going to be impulse response. For our filter, right? So let's see how it looks, if everything works correctly, if there are any mistakes. So yes, we can see that we have somewhere here syntax error. That's probably because I didn't close all the brackets. Yes, that's indeed. So as you can see, I have opened this bracket, but didn't close it after calculating the entire denominator. So this bracket is closed by this bracket, yes, but this doesn't have any pair. So I need to close this bracket here. Now you can see it marks which it matches, yes. So now it should work. Yes, now we can see this discrete representation of our, how to say it, impulse response. Yes, in our lecture, we have described it as an analog process. So that was connecting all these dots. But in computer, we have discrete process. We have digital process. Yes, so basically, this is number of symbols we have. So we have symbol 1. Here we have symbol 2, symbol 3. Symbol 4 is at 30 milliseconds, so somewhere around here. Symbol 4 is here, and symbol 5 is accordingly ending here. Yes, so basically this is symbol 1, symbol 2, symbol 3, symbol 4, and symbol 5 in between these samples, right? The same goes into other direction. Now, in this symbol 1, we have 1, 2, 3, 4, 5, 6, 7 samples, which is my value, right? So I had 7 samples per symbol. That's exactly this number. Now, you may also note that we have actually here 100 value. Well, that's because in digital case, we actually need to normalize it also with the number of samples, right? To be more specific, I believe this maximum value is not actually 100, but no, it is 100. Yes, I believe. We can actually find it out. Maximum HRC. Yes, it's exactly 100. It's in fact, believe, and yes. So sampling time divided by NSMP, right? So here, actually, what we needed to do is to divide the with sampling time and divide with number of samples per symbol, like this. All right. So then maximum value should be 1. Okay. Didn't change. Wait a minute. I actually have achieved this. So I believe if I remove this, it's going to be 1, right? So I need to actually remove this at all, right? Like this. So this formula was specified for continuous time process, right? And here we have some changes when we work with digital signals. So now we have here maximum value of 1. Yes, and this is our shape of the impulse response. Here we have a 0 time interval, and our delay is going to be from here to up to here, right? So basically, this number of samples is going to be our delay, which is exactly half of the impulse response except for this central node. Now, however, considering that we have complete symmetry here, this is going to be odd number anyway. So if we divide this total length of the impulse response with 2 and take the lower part, yes, then we are going to find our delay. So let us find this delay, right? Now I believe we can replace stem with plot function so that it looks like as if it is continuous time process. So now it will be connected with line. Now this line is quite rough, but it can be improved by changing the number of samples. So you can see that for your case you have more samples than 7. So I'm going to put minimum of 11 just to show how this line improves. Yes, for 21 it's going to be very smooth, like this, right? But you need to do what is given in your parameters. So in my case, it's not maybe smooth, but if I reduce the picture, so it's going to look better, right? So that's this line. Actually, as you can see, it completely matches what we have here, right? Only here we had for 3 symbols, now we have for 5 symbols. Now, this time, however, doesn't really represent correct values. So we need to actually, for plotting purposes, have other time. Yes, so for plotting purposes here, we need to show real time. Let us calculate it accordingly here, the real, as starting from 0 and going up to double number of symbols multiplied by symbol time with the step of the sampling. So that would be plotting time. Because we cannot really work with negative time, right? So here we start with 0, and here you can see what is going to be our delay. That is 50 milliseconds, right? So now let us, however, instead of strict delay in time units, we are going to need delay time expressed in number of samples, right? So let us find this delay. Wait a minute. We actually didn't finish because for some of you, depending on the beta parameter, it might be necessary to actually calculate some points because otherwise you might get some infinity. Yes. So let's try and find such case. I don't know. For example, if I have here 0.1, I don't believe I have any infinities here. Yes. So everything is in order. But you may have noticed that these side values have decreased, right? So let me again return 0.6. Yes, now they are larger oscillations. Now I'm going to put 0.25, for example, and it still looks fine. Actually, let us find what time we might experience problem, because the formula specifies this value, right? So the formula says that we need to do that for time at t symbol divided by double beta, right? So I'm going to calculate that time, t symbol divided by 2 divided by beta, and it is exactly 220 milliseconds, right? So that means that here 0, so here at minus 20 milliseconds and here at plus 20 milliseconds, I might have incorrect values. So let's check if these are normal numbers. Everything is fine here, but again, it sometimes might calculate incorrectly these values, just because there is a division with 0 possible. Now, in my particular case, I didn't really have this 0. I had, rather than that, some very small number, as you can see here, yes? Because computers have limited accuracy, right? Some specific number of symbols after the decimal point, and therefore sometimes what we expect to be 0 is not really exactly 0. So with this number, computer can divide, yes, actually, another small number and calculate something, yes, but if it is strictly 0, then in that case, it's going to have infinity. Yes, I still haven't found an example of this, but it is, I believe, still possible. Let us change this number of symbols maybe to 3. Just to see if it works like that. And 24 maybe. No, it's difficult to find when exactly it will happen. I did happen to see it, so I know for sure that it can happen. Yes, but at any rate, I don't remember what parameters I used to actually observe the situation. So just to be sure that nothing wrong happens, we are going to actually add this additional condition, yes, for this specific case, for plus and for minus. How do we do that? So at the beginning, we are going to find if we actually have this case when time t, actually let me return my values here, 0.6, and here I had 5 symbols, right? So first of all, let us check if we have encountered any of these, well, values in our time, because it also may depend on sampling, actually. Yes, if we do not happen to hit precisely that value when we have 0, it's not a problem, yes? It's not a problem if we don't happen to hit that point precisely. This depends on specific point, yes? So let us start by finding all these points. So t symbol divided by double beta. T symbol divided by double beta. Now, what we do here is not actually say that t is equal to t symbol, but we ask to check if any of t elements is equal to this. And as a result, we have this returned, yes, which denotes with symbol 1 any position when we have this observance. And as you can see, not a single value is actually equal to this. So test symbol divided by 2 divided by beta is this number, right? And if I output my t, I can see that there is no such number at all in my particular case. So that would be 8. So here I have 4, 5, 7, 8, but it's not 8333, right? And therefore it's okay. I didn't happen to hit this number. So now I know that I need to actually have this number. And again, maybe like this. Symbol time like this. Just to see. No, not really happened. Like, okay, maybe 9. So no, yes. So I'm lucky. I'm just lucky not hitting this particular number. Again, I might change beta to 0.5. In that case, I'm going to need to hit this number. Yes, and it's here. Yes, you can see clearly that it is present here. But I don't think we have here any, how to say it, interruption in functions. So let's see Asher, see if there is infinity. And there is none, no infinity either, right? So let's make 10 maybe. So as you see, sometimes it happens, sometimes it doesn't, just because the accuracy of calculations is important factor here. But either way, in order to be safe and avoid any problems, so we are going to check this condition. And as you can see, although I have these numbers, yes, I have it here and I have it here. They are not exactly completely same because this check didn't find any differences. Yes. Now, if I check for 0, for example, then you can see that indeed it has found a strict complete 0. So that means that this is not exactly 001. Yes, it's some other numbers in the end. So we were lucky here, but again, it may not be like this forever. So for that reason, we are going to add this extra precaution condition, right? Because it's not that hard to implement. So we are going to say that for any HRC value, when t is actually equal to the symbol divided by double beta, we are going to replace it with this formula. So that is p divided by 4 divided by t multiplied with sync 1 divided by double beta. There are no vector values here, so I use regular multiplications, right? The same goes for negative minus tsim. Yes, this is just a precaution, and actually it shows how I achieved this, well, how to say, piecewise representation of the function in Octave, right? So I have 3 pieces here, and basically I have covered all the possible cases by this theoretical formula. Okay, so now our function is ready. I'm sorry, I have to use the symbol here. Error. The impulse response is completely symmetric. So what we want to do now is to actually make one of our tasks of how to say it, displaying response of the channel. So this is a filter, yes, and this filter is the model of our channel. So now we want to draw two more plots, one of them showing amplitude frequency response and one of them showing phase frequency response, right? So to do that, we need to use Z transform. Yes, so Z transform replaces in our filter expression. So basically we have our filter expression specified like h0 plus h1 z minus 1 plus h2 z minus 2 and so forth for as many symbols as we have, and we have 71 of them in total, right? And we need to actually replace this with a power of j omega t, where omega is from 0 to 1 or p in MATLAB case, right? And accordingly show the plot for each of these points for complex module, complex number module, and complex number argument. Yes. So basically we are going to do that now by using so-called fracuz function. Yes. So help fracuz. This exactly does what we need by replacing each z with this range of frequencies. Yes. And the result, it produces the complex frequency response H capital. So let us do that here by calculating a complex frequency response. So here, this way, you also get familiar to how you can actually check filters frequency response. What you need to do is, in general, our frequency transfer function in Z form for any type of digital filter is specified like this: A0 no, B0, even capital B, right? B0 plus B1 Z minus 1 plus and so forth plus BM Z minus M, and in the denominator we have similar for A0 plus A1 Z minus 1 plus so forth plus A n Z minus n. In general, not always n is the same as m, but it must be at least the same. It cannot be smaller than m, right? For this filter to be stable. Now, we have vector b consisting of the elements of b0, b1, and so forth up to bm. We have vector a consisting of similar coefficients without these z values. Yes, so we in MATLAB we only specify these values, these variables before this function variable z. Yes, so these are vectors. Here we have commas, and here we have 1. Yes, and an. We put them in here. We specify the range of frequencies where we want to calculate, and as a result, we get this frequency response. So let's do it. Yes. For that to happen, we need to know frequency range from 0 to, with a step of 100 parts, to Nyquist frequency, which is sampling, half of the sampling frequency. Normalized form, it is 1. Yes. And here we calculate it as fracuz. Now, for our fear filter all the A coefficients. Well, basically, just let us say so. A are like this. 1 and then 0, 0, 0, 0, 0, 0. So basically it's the same as 1. Now for B coefficients, these are actually our impulse response values. Yes, so this is going to be accordingly HRC minus N, HRC next minus N plus 1, and so forth. So this is actually our HRC. So let us write them in here. HRC, here it's 1, and the frequency range in which we want to calculate is omega. However, this frequency range for frec_uz function must be in range between 0 and p. However, for us, usually it's more convenient to have it in range from 0 to 1. That's why here we have specified it in 0 from 1, but here we are going to multiply this p just so this function works correctly. Yes, so here we calculate complex response. Now we can plot them. How do we plot multiple figures in the same window? For that we need to use a subplot command, subplot, and we are going to have 3 plots organized as follows. So that's going to be our plot 1, plot 2, and plot 3. Here we have this impulse response. Here we're going to have frequency response, amplitude, and here we're going to have phase frequency response, which I remind you must be a linear function. And that's when we are going to see that indeed it is, right? So there are going to be 3 plots in this dimension, 1 plot in this dimension, and numbers 1, 2, and 3. So this subplot function accordingly specifies number of rows, number of columns, and the number of specific plot currently being active, right? So this is 3, 1, 1. The next plot we are going to plot is going to be 3, 1, 2, right? So basically the first 2 numbers specify the array of plots, and the last number specifies the number of plot being displayed. So there we are going to have omega on x-axis, frequency, normalized, yes, and on y-axis we are going to have absolute value of h. Yes, again grid on, again x label, that would be normalized frequency, and the y-axis label is going to be amplitude response. So let's see how it looks like. So as I said, it is not brick function, but has a slow transition to 0. Yes. And in fact, the speed of this transition depends on beta parameter. Now I specify beta equal to 1. And it became slower. I specify beta equal to 0.1. And it's, first of all, more steep, but also you can see that now we have some ripples here. It's no longer a constant, which is not so nice. Yes, because as you remember, for ideal channel, we need to have here a constant level. Yes, now you can clearly see that we do not. So if I set 0, which theoretically would produce me completely rectangular brick type function, yes, with complete 0 here and completely constant level here. But in fact, it's going to be, well, disappointing for us, right? Because it's not really much different from 0.1. Yes, it has these ripples. It's not steep. With this function cannot generate a really rectangular shape as it's in theory, right? So we have met some practical limitations, mainly because our impulse response is finite. Yes, in theory, this impulse response must be infinite. So basically here, number of symbols must be infinitely large, but we cannot really work with infinitely large. Yes, unfortunately. So that's why we have this result. Now, next plot is going to be phase frequency response. So I'm going to copy everything here, name it phase response. This is accordingly going to be third plot, and instead of absolute value, I'm going to show here angle, yes, argument of the complex number. But as you can see, here we have some unclear things, yes. Why does it happen to be so? So help angle. As we can see, the angle additional help on built-in. Okay, maybe let's try that. Doc angle. Yes, there is additional help here. And it calculates the argument of the complex number. Yes. And here we should see that this argument is returned. See also arc. Yes. Maybe it will work correctly. But the idea is that if we watch it from the plot, that the result is returned in range from minus p to plus p. And clearly, for linear function to happen, it has to go like this, right? But in order to keep it in range, this automatically converts minus p to accordingly plus p, yes, by adding 2p to this value. Yes, you know that changing the phase by 2p, 4p, and so forth doesn't change really much. So basically, this is difference of 2p, right? And it accordingly does that. There is a function that removes this effect. Yes, but first let's see if argument arg function will help us. No, arg function produces exactly the same. And as for help arg, it doesn't say us either what is the range of the output, but this range is clearly seen from figure is from 0 or from minus p to p. So for that reason, we are going to use the function called unwrap, help unwrap. Yes. So you can get help on each command. So unwrap adds or subtract multiples of 2p so that it removes these jumps. Yes. So basically, what we can do is use it in addition to this arg function. So unwrap arg h, and this unwrap has to remove all these extra additions and make this line linear. And indeed it did. Yes, of course we can see that outside of the frequency band it is not linear, but for that we don't care. Yes, what is important is that within this bandwidth, which is our delta f, right, this function is ideal linear function. Yes, you can zoom it and see for yourself that this is a straight line without any changes and stuff like that. This is possible only for finite impulse response filters, right? And well, we have successfully solved that problem. So, what I wanted to check here. I need to return my beta. And as you can see, for other betas, it also remains linear. So that means that we have successfully made this filter. That would be our first task. And the second task would be to actually make it work with our data. Yes. And I believe that we need to take a small break, maybe. Yes. Yes, I believe the break is in order because we are more than an hour already talking about this. And we will continue after a break of 15 minutes, right? So we'll start with your questions. If you have any questions, we will start after 15 minutes with questions, right? So if something is not working, we will be able, I hope, to help you with that.
Can you please leave the MATLAB window open, like maybe for a little bit? Not this software that we are using, just maximize the window. So I'm trying also to do
This you mean, yes?
Yes.
To see the code. Okay, no problem.
Thank you.
So see you in 15 minutes then.